Okay.
And then we're going to introduce the next speaker. And the next speaker needs no introduction. Jeff Taylor. So I've learned a lot from Jeff, and he doesn't believe that. I think many of us have learned a lot. And you're going to switch gears and tell us about water in the interior.
Yeah, can water escape from the interior? And this is a topic that came up at this really inspiring workshop that survey workshop held in November. It was organized by Dana, Yvonne, Carly, others. It was really interesting. One of the topics that came up is how much water could be escaping from the inside. And a lot of this came up because we thought there was water at the poles when we thought the inside was completely anhydrous. And so it is an interesting thing to consider. So what David and I have done is to do a feasibility study asking the question, first, can I have the next slide? First, what is the inventory of water inside the moon? And then, and it turns out there's a lot of water in the moon in terms of absolute mass compared to the amount we have at the poles. But does it leak out? And I'm going to just briefly mention the stability and state of water in the moon, not get into that. That does need more work. And then finally, I want to talk about water migration triggered by moonquakes. Let me just point this out now. The most efficient way to get water and any other volatile from inside the moon to the surface is by magmatic activity. And I'm not going to talk about that because I'm worried about things that's happening now, which is to say in the last 1 billion or 2 years, when magmatism has decreased substantially. It is still worthwhile to look at how much escapes from magmatic activity, and we'll do that next. But for now, I'm going to worry about a moonquake mechanism. Next slide. Okay, I'm going to show 2 slides with a lot of numbers on them. The only thing you have to look at is the exponent next to a 10. And so we got Mare basalts and pyroclastic deposits and their intrusive equivalents. So to skim over the numbers so that you do not scrutinize too carefully, there's a volume of Mare basalts, there's a mass of those Mare basalts, there's a concentration of water in those. You'll see I use concentrations that are 10, 100, or 1,000. It gives you an idea of the precision of this talk. And the Mare basalts, this volume is well established, and assuming that the crustal component of Mare basalts lost 95% of it, which may have made an atmosphere, as Needham and Kring point out in an interesting abstract last year in the paper submitted, you end up with, in the crustal component, 1 × 10⁻⁴ kilograms of H2O could be contained in them. However, the intrusive amount doesn't lose anything, and I'm taking it as double the extrusive volume. This could be 6 times. There are work done on terrestrial intrusion versus extrusion in volcanic systems. And so it could be 6. I'm taking 2 because it just seems more logical for the moon, and with lower gravity, a bigger, well, there's a lot of reasons for doing it. Feel free to change that any way you want. And this ends up producing 5 × 10⁻⁵ kilograms, assuming 100 ppm in the magmas. Pyroclastic deposits have a lot more water, but there's not much of them. If you take the ratio of the area covered by pyroclastic deposits to Mare basalts, assume the pyroclastics are 100 meters thick, which is actually, I think, generous, and 1,000 ppm, that is actually the one number I will give you that's pretty well established from melt inclusions in olivines in orange glass and loss of 98%. You get very little, actually 10⁻⁴ kilograms in the crust. But the intrusive volume is 10⁻⁴, is still much less than that because the volume is so low. Next slide. There are intrusive rocks we call the MG suite. There's creep basalt equivalents of them. How much of that is there? I will tell you how much. It is the entire crustal volume of the Procellarum creep terrain. Feel free to not agree with that. But if it's 100 ppm in those, and I think I actually could justify that, the water mass is 4 times 10 to the 16th kilograms. The highlands have very little water in it, but they are enormous in volume. There's 5 ppm, measurements have shown recently, a good paper by Hue et al. They give 6 ppm in plagic clays, so if you take 5, because it's more in keeping with order of magnitude calculation, you get 1 times 10 to the 16th kilograms in the highlands. Not a high concentration of water, but the total mass, because the highland mass is so big, you get quite a bit of it. Next slide. So the answer is there is something like 6 times 10 to the 16th kilograms of H2O in the crust, and the polar cold traps contain 2 times 10 to the 12th or something like that, the estimate is. So it's 10,000 times bigger. You would say, well, that seems like a reasonable source, but the key question is how much of this leaks out? So next slide. I'm going to talk about how it might leak out. First, the question about stability. I claim that in the intrusions, actually the water really ends up being stable. There's not enough water concentration to make a separate exsolved fluid phase. There may be reactions with the surrounding country rock when intrusions come in, but I think it's probably pretty stable. However, the crust has been greatly bombarded, as shown, I think, really well by not only all the craters drawn, basins and craters on this, but this is a map of porosity derived from Grail data. And the average porosity is like 10 or 12%. That suggests that the crust has been greatly reworked, and there's been a lot of but due to the early bombardment, and therefore it has loosened up the water that might have been quite solidly bound in, say, apatite, so that it might be easy to have it migrate, say if you have a moonquake, and it could migrate from fault zones, and that's what I'll consider next. Next slide. Now, escape of volatiles, and especially noble gases, because they're easier to track in terrestrial faults, there's a big literature on it. It's very interesting, of great interest, because it is thought it could sometime give us a precursor warning of an earthquake about to take place. And to show that point, this is a diagram that shows time in an experiment that has the stress increasing on a sample versus the amount of helium released. It's radiogenic helium. This is the helium curve. The others are various stress in different directions. The important thing is, it is at this line here that the rock fractures catastrophically, but notice that the helium leaks out before that, and it is thought, and notice the stress begins to go down, thought that this is due to intragranular microfractures. So this mobilizes gases even before the moonquake would take place. So I contend that water might behave the same way. It might be in form of hydrogen or OH as well. And so before the fracture takes place, and then once it takes place, it releases the gas. It's a pretty effective mechanism. Next slide. So there are lobate scarps on the moon, which are thought to be the surface expression of thrust faults that go down quite deep. I am going to take, I'll show you a number in a minute, but I'm just going to take the fault is the entire depth of the crust. And so you get this, there's a zone in here that would be crushed up during the moonquake, or in series of moonquakes, to release water from the moon. There's a lot of these things. Next slide shows a map from a paper by Waters et al. And all the little red dots, which are actually slashes, show the locations of these lobate scarps. There's like 3,200 of them, all of which are less than about 100 million years old. So it's like an ongoing process on the moon. These things could all be, not all, when they move, release some water to the surface. How much? Next slide. Well, we can make one estimate from argon. Argon 40 was measured, has been measured in by these instruments. This is argon source release from the LACE instrument, and ignore this line here, but notice these are moonquake times here as detected by the seismometers on the moon. Notice there's a pulse of argon with that moonquake, and this one. The machine was not turned on yet for this, and yet no moonquake detected for this one. So perhaps there are other mechanisms, or perhaps the moonquake was just not detected for some reason. This is the instrument called LACE that was carried on Apollo 17. This is the link to moonquakes releasing volatiles from the moon. Next slide. So I made an estimate from argon-40 released and a ratio of that to water. This is not well known, and the amount released, this is the estimated by Grava et al., about 6 times 10 to the 3 kilograms per moonquake. The water released to argon ratio, which you need to know, is big range here based on LACE versus the side instrument, which is the superthermal ion detection experiment, and which was carried by earlier Apollo missions. And so I'm going to bracket it with these two numbers. This could be nice to know this better. There's potassium in the crust. It decays to argon in the crust. That's how much there is. So you have this much argon in the crust, and you have this much potassium in the crust, and you take this much water in the crust, which I just showed you. You take the ratio and the moonquakes, and you get these two ranges per moonquake. And the next slide shows, if I did this diagram myself. There is a length of the fault plane, which is given by the distance along surface of lobate scarps. There is a depth, which I take equal to the depth of the crust. And the scarps range from 0.5 to 22, so I just took a range in the middle. I have 10. And there's a concentration of water, which I take to be simply 100. And then there's an angle here that gives this distance here with the depth. There is a thickness there that matters, and I take that as the thickness of the typical fault plane. And on the Earth, they range from 10 to 150 meters. So I'm taking it as, I'm going to use all of those, as you'll see in a second. So you can get, there's a volume in here that is affected by each moonquake. Next slide. So here this is water release in kilograms per year against the thickness, the width of the fault zone. The thicker it is, the more water would be released. And these curves are for if we lose over the lifetime of the fault, which I take to be 1 million years, 1%, 10%, and 100% of the water. You get, and there is a shaded region here. It isn't coming out so much. This is the region based on argon. It's here. I don't know if it shows up better from a distance. But anyway, so if you take 10 to 100% loss from each moonquake, and you have 5 a year, they kind of correspond with the argon number, and you could get something like 10 to the 2 to 10 to the 4 kilograms per year released by this moonquake mechanism. And that would sound pretty low, but in 1 billion years, you would release 10 to 11 to 10 to the 13th kilograms, which brackets the amount we think is in the poles. But that takes into account no loss. And that is completely unrealistic, so that this number actually is kind of modest. Next slide. So here's the conclusions of this. The interior water releases just 10 to the 2 to the 10 to the 4th kilograms per year. In comparison to solar wind, again, we're not taking this as a source, not worried about the losses yet, is something like 10 to the 13th kilograms per year, which I took from a paper by someone named Kreider and Vondrak. And from asteroids or other meteoroid things, it's something like from this paper by, it's an abstract, but it was the one I found. I may need help to get better sources of this, something like 10 to the 7th kilogram per year. So there's a big range in here. This one clearly dominates, but this one is interesting but kind of weak. This does not mean, let me emphasize again, that water could not be delivered by young magmatism, if there is any, or sufficient. And that is something that's still worth looking into, and we haven't done that yet. There's uncertainties. You might have noticed there's uncertainties. How much water can diffuse to the surface? And probably not much. The diffusion rates are low. It's a great paper by Rosemary Killen in 2000, I think, 2003. Read that paper. It really goes into how much water can be lost, diffusive mechanism, and the role of, in fact, microcracks, including mentioning moonquakes. It's a very good paper. How much of the water is released, whether it's moonquakes or diffusion, how much comes out as hydrogen or H2? And that's an important thing. What's the partitioning? And is it even possible that actually you do leak out hydrogen and helium, hydrogen or molecular hydrogen, and not water, because one is bound more than the other? I don't know that either. And what's the typical lifetime of a fault producing the 3,200 observed ones? So anyway, thank you. The bottom line is interior water by the Moonquake method is probably interesting, but doesn't seem to be an important source of water to the whole surface exospheric system. Thank you.
We're going to move on to the next stuff.